Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up our introduction to basic probability by actually formalizing a couple basic probability rules and looking at a couple of examples. Also, at the end of this video, we'll take a small glance at a connection, one of the first connections we're going to see between probability and the more data-driven side of statistics. So let's start off by talking about a couple rules. We've actually briefly mentioned these already in some of the previous examples, and to be honest, we've even used them several times, just we didn't formally state their name or their sort of formula here. So let's go ahead and take a look at these rules. First is the complement rule. So the complement rule basically tells us how to calculate the probability of an event not happening. Normally we're calculating the probability that something does happen, but sometimes we might want to calculate the probability that it does not happen. And the complement rule says that the probability that an event does not happen is 1 minus the probability that it does happen. And while that might seem a little complicated when it's in sort of a formula form like this, this is something as a rule that we all already know. If, for example, you hear that there's a 20% chance that it is going to rain today, we intuitively know that that means there's an 80% chance that it's not going to rain. Why is that? Well, because if we think about this in terms of percentages, that 1 is the same as 100%. So by saying that there's a 20% chance that it's going to rain, then 100% minus that 20% gives us the 80% chance that it's not going to rain. So the complement rule is something we intuitively understand. Now, in practice, sometimes like we've seen in some of the past, and we'll see in some of the examples coming up, you can use the complement rule, but you don't have to, right? You can also just figure out directly all the ways that something might not happen. And as we'll see, sometimes that's a viable option, but sometimes that'll be sort of very complicated, especially as we move into advanced probability, that it'll be easier to actually apply this rule. Let's take just a quick look at a visual example to help us sort of understand the complement rule. So here's a collection of little different colored, maybe they're like marbles or something, and let's just imagine very simply we're choosing one of these at random. So we want to calculate the probability that it's not blue. So one way, of course, that we could do that is we could try to go ahead and directly just count up all the things that are not blue. So of course we could say, well, there are 4 reds, there's 1, 2, 3, 4, 5 greens, that's 9, and then 2 purples, that's 11. So we could say that this probability is 11, and then I guess out of the total there's 4, 7, 12, 14. So we could get this just directly as 11 out of 14. But an alternate way, using this complement rule, again, you don't have to. I mean, we just calculated the probability, so we know we don't need to use the rule. But notice it's a little bit faster to say that the probability that it's not blue is 1 minus the probability that it's blue. And do 1 minus, notice then we only have to count up the ones that are blue. That's 3 out of 14. Treating this 1 as 14 out of 14 to make a common denominator, well, then we get 11 out of 14. Visually, why does this work? Well, what we're doing here in sort of using the complement rule is saying that there's 14 things overall. Get rid of all the blue ones. Well, 14 minus 3 gives us the 11 things overall. So that's all the complement rule is really saying. Again, in the examples we'll be doing today, we'll sort of see that the complement rule is optional. It can be a nice trick to speed things up a little bit, but it's not necessarily necessary. However, as we go further on and the sort of probabilities that we're calculating get more complicated, it'll be really important to be able to use this rule. So you should really think about this sort of, when we're doing these examples, as getting to practice this complement rule, so in preparation of needing to use it later on. All right, let's look at another probability rule called the addition rule. And this one we've encountered a bunch of times already without ever formally mentioning it. We even learned about it way back when we first started descriptive statistics, and we were calculating percentages and mentioned like the percentage of individuals that fell into one category or another. And we sort of talked about how in mathematics, or is usually associated with the addition operation. So the addition rule formally says that the probability that event E or event F, so either E or F happens, we don't care which one, as long as one of those happens, one or both of them happen, then we can calculate that probability as the probability of E plus the probability of F minus the probability that they both happen. We've encountered this many times, as mentioned before, and what this basically says is that when you have OR, you get to add them together, but you have to make sure you don't double count. And this subtraction of P of E and F basically handles that double counting. So again, let's take a look at a little visual example. Let's imagine that we're choosing one of these things at random. So these things are different shapes, squares or circles, and different colors, reds and blues. So let's imagine we choose one at random. So let's try to calculate the probability we end up with something that is either red or a square. Now remember, when we're doing things mathematics with the word or means that we will have gotten what we want if we get something that's red. We'll have gotten something we want if it's a square, and we'll get something we want if it's a red and a square, right? So or here means one, the other, or both, right? So as long as at least one of these things happen, we've satisfied this or event. So again, the sort of manual way to do it would be to count up all the reds, 1, 2, 3, 4, 5, and then count up all the squares that we haven't counted, 6, 7, 8, 9. And then, of course, we'd look at the total. We'd say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 objects overall. So this probability would be 9 out of 12. And again, we got this numerator of 9 by saying let's count up all the reds, 1, 2, 3, 4, 5. And then all the squares that we haven't counted, 6, 7, 8, 9. So 9 out of 12. What this addition rule would allow us to do is the addition rule would say that the probability of red or a square is the probability of red plus the probability of a square minus the probability of red and square. Okay, so what would we get there? Well, probability of red would be very easy. That would just be 5 out of 12 plus the probability of square, which would be these guys, right? All those things are squares. That's 7 plus 7 out of 12. Minus the overlap, the red and the squares, which would be these 3 here. So minus 3 out of 12. What happens when you add those together? 5 and 7 is 12, minus 3 is 9. So of course you get the same thing, 9 out of 12. Visually, what's sort of going on with this? Well, what we're doing to count up all the things that are red or square, we're sort of saying there's all the reds, there's all the squares, and notice that these things are the overlap. So we have to make sure to subtract that overlap so it's not double counted. We want to count it once, but we don't want to count it twice. And unfortunately, when we take all the reds and then we take all the squares, we do end up double counting. So by subtracting that overlap, we avoid double counting. All right, speaking of double counting, there's some situations where you don't need to worry about double counting because the events don't have any overlap, and we give that a special name. So two events, E and F, are said to be mutually exclusive. Sometimes you will also see that mentioned as disjoint. So mutually exclusive and disjoint, they mean the same thing. Mutually exclusive if they cannot happen at the same time. Notationally, what this means is that the probability of E and F equals 0. So if the two events cannot happen at the same time, then the probability that they happen at the same time must be 0. Because remember, a 0 probability means that what we're talking about is impossible. Now, why do I mention this? Well, this is exactly the situation when there is no overlap. So we give something that sometimes is referenced as the special addition rule. What the special addition rule says is that if E and F are mutually exclusive, then to calculate the probability of E or F, you just simply add the probabilities. Notice that this rule here is the same as this, just without this component. Why can we just delete that component? Well, again, because we're in this special situation where we're assuming they are mutually exclusive. Remember, if they're mutually exclusive, the probability of E and F is 0. So this right here would be 0, so we don't need to worry about it. So in general, when you're looking at probabilities of two events, E or F, you need to add and then subtract any overlap. If you know that the two things cannot happen at the same time, then you are safe in just simply adding them together. And we've used the special addition rule many times when we build the probability model, because every outcome is disjoint or mutually exclusive from the other outcomes. So we were safe in just adding those probabilities. But in general, if you just choose two random events, you do need to be careful that if you're going to add them, you have to subtract any overlap. Okay, so this sort of page here gave us two probability rules, the complement rule and the addition rule, as well as this extra definition of what it means to be for two events to be mutually exclusive. We're going to do a couple of examples now where we'll get to practice these rules, as well as just practicing calculating basic probabilities. And as we do this, we'll also make sure to reference and try to use this new terminology of when are we using the complement rule, when are we using the addition rule, and if we encounter any mutually exclusive events. So let's get into our first example here. So for this example, we're going to suppose that we have 9 people in a room. So for each of these people, we know their name and their gender. So we have Aaron, Andy, and Annie. So Aaron and Andy are males, Annie is a female. We have Bob, who is male, Carl and Cindy, Carl who's male, Cindy who's female, Danielle, female, Donna, female, and Emma, also a female. You'll notice that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 people as mentioned. We're going to suppose that we select one person at random from this room. So we're taking one person from this room. We're going to calculate each of the following probabilities. Now again, one of the key things we should always make note of here is, as we know, there's 9 total. So each of these people has an equal chance of being selected. So that means everything's going to be out of 9 because our sample space is size 9. Okay, what is the probability? You get somebody who's female. So probability of female. Now notice there's no ands or ors or nots, so we don't need to use any special rules. We can just calculate this. So how would we do this? Well, we'd figure out how many outcomes satisfy being female. Well, there would be 1, 2, 3, 4, and 5. So this probability would be that there's 5 outcomes that satisfy the event of being female out of 9 total outcomes in the sample space. So this probability would be 5 out of 9. What's the probability for B, that the name starts with C? Again, we just look through how many outcomes satisfy the name starting with C. Well, if we select Carl or Cindy, the name will start with C. So that's going to be 2 out of 9. All right, let's look here. The probability we get someone who is male and whose name starts with A. So male and starts with A. Okay, again, remember, and in mathematics means that these people have to be males and they have to have their name start with A. So they have to have both of these traits. So in terms of males, we know that there's Aaron, Andy, Bob, and Carl. But of course, we also want them to have their names start with A. So only Aaron and Andy will satisfy that. So this will be 2 out of 9. And those 2 people, again, are Aaron and Andy, the only 2 people that have both of these traits. Okay. For D, you get someone who is female and whose name starts with B. So probability female and starts with B. So we want somebody who has both these traits, who is female and whose name starts with B. So we can see that for females, we have Annie, Cindy, Danielle, Donna, and Emma. None of them have names that start with B. The only person who has a name that starts with B is Bob, but he's male. So that means there are no outcomes that satisfy this. So we'd say that this is 0 out of 9, which of course we could simplify to just saying 0, meaning that this is an impossible event. There is no way that we are going to select someone who is simultaneously female and whose name starts with B. This would mean, in our new terminology, that the events female starts with B are mutually exclusive, and sometimes we'll abbreviate mutually exclusive as capital M period capital E. So these are now, this pair of events is an example of mutually exclusive events. Whenever we talk about mutually exclusive, we're always talking about a pair of events. So it doesn't mean that female is mutually exclusive. That doesn't make any sense. We're saying that female and starts with B are mutually exclusive. There's nobody who has both of those traits, at least in our room. All right, now we get someone whose name starts with B or D. So probability starts with B or starts with D. Okay, so we know that there's an OR here, so we know we're going to be doing some sort of addition. For starts with B, let's go back and see. There'd only be one person who starts with B, that's Bob, so we know that that's going to be 1 out of 9, plus starts with D. For starts with D, there's 2 people, Danielle and Donna, so plus 2 out of 9. Now, do we have to worry about any overlap? Do we have to do a minus people who start with B and D? Well, there is no one, right? You can't have your name start with B and have it start with D. You can only have it start with one letter. So we don't have to worry about any overlap. We can just add these together and get 3 over 9. Notice that what we just used here was an example of what we called the special addition rule, where we said the probability of E or F is just probability of E plus probability of F. The reason we were able to do that is, of course, that the idea that they start with B and the idea that they start with D are mutually exclusive. So right here we can also make a note. Starts with B, starts with D are mutually exclusive. So since there was nobody who could start with both of these, we were able to just add the probabilities and we were all good. All right, we get someone who is female or whose name starts with A. So now we want somebody who is female or starts with A. Okay, so we're going to do some sort of addition. So let's find everybody who is female. So we know that that was Annie, Cindy, Danielle, Donna, Emma. So that's 5. So we're going to take 5 out of 9 plus everybody who starts with A. So if we see here, that would be Aaron, Andy, and Annie. So that's 3 out of 9. Now, was there any overlap? Was there anybody who was female and who started with A? Well, there was, right? There would be Annie, and we basically double counted her, right? She was counted once when we counted up the 5 females, and then she was counted again when we counted up the 3 people who started with A. So we need to subtract that overlap, that minus 1 out of 9, which is just making sure that we don't double count Annie. If we go ahead and we do that, 5 plus 3 minus 1, that's going to be 7 out of 9. Now, just for fun, I mean, obviously this is correct, we're good here, but let's just go through, and if we just count carefully without double counting, we should get 7 out of 9. So remember, we're looking for female or starts with A. So for female, we'd say Annie, Cindy, Danielle, Donna, Emma, and then starts with A, Aaron, Andy. Notice we wouldn't underline Andy because she's already underlined. So notice that's 1, 2, 3, 4, 5, 6, 7. So 7 out of 9. All right, finally, you get someone whose name does not start with C. So probability does not start with C. Well, we can use that complement rule. We can say that's 1 minus the probability that they do start with C. So starting with C is easy. That's only 2 out of 9. So we do 1 minus 2 out of 9, which is 7 out of 9. And again, that's just treating this as 9 out of 9 to make a common denominator. So we have 7 over 9 there. Now, what if we just go through and we carefully avoid everybody who does not start with C? We should still get 7 over 9. So we would say, okay, Aaron, Andy, Annie, Bob, Danielle, Donna, Emma. Yep, that's 1, 2, 3, 4, 5, 6, 7. Avoiding the people with C. So again, you don't have to use these rules right now, right? You can just sort of be careful about counting and looking at your sample space. But again, as we go further, the rules are going to become more and more useful. So now is a good time to practice them. All right, so there we go. There's a basic example going through calculating probabilities using a little bit of sort of our terminology. Notice these pairs of events, female starts with B, were mutually exclusive. Starting with B, starting with D were mutually exclusive. But pairs like female and starting with A, they were not mutually exclusive because there was Annie, who was female and started with A, which is why we had to subtract that when calculating to avoid that double counting. All right, let's try a similar example. It's a little bit more complicated because the sample space will be a little larger, but it is also a very common probability situation that we've probably all encountered before. So we're going to talk a little bit about cards. Give a quick definition because sometimes people think there's different things in a deck of cards. We're going to, for our class, talk about what is a standard deck of cards. So a standard deck of cards has 52 cards, so that means the sample space or the size of the sample space is going to be 52. These cards are made up of 4 suits. So the suits are hearts, diamonds, spades, and clubs. Usually we sort of denote hearts and diamonds as red suits and spades and clubs as black suits. So there's 2 colors, red and black, and then inside of red there's 2 suits, hearts and diamonds. Inside of black there are 2 suits, spades and clubs. Each suit has 13 different types of cards. These are the number cards, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all of these sometimes 2 through 10. These are called number cards. Then there will be a Jack, Queen, King. So these 3 are often called face cards. And then the 13th and final type in each suit is an ace. So, in other words, there is 1 2 of hearts, 1 3 of hearts, 1 4 of hearts, so on and so forth. There's 1 2 of diamonds, 1 3 of diamonds, 1 4 of diamonds, so on and so forth. So there's 1 of each of these types for each of these suits. And notice that that does give us, by multiplication, 13 types times 4 suits gives us 52 cards overall. If you ever see a deck of cards referenced in our class, we mean a standard deck of cards, unless the problem specifies some special deck. So if you ever just see a deck of cards, it means a 52 card deck with these suits and these types. So for this example, we'll make use of this deck of cards. We're going to suppose you draw 1 card at random from a standard deck of cards, and we're going to calculate the following probabilities. So notice I put these already in the probability notation just to make sure we're comfortable with that. The first probability we want to calculate is what is the probability that we draw out a 7. So let's think about how we would do that. What is the probability of a 7? Well, we can say that there are 52 cards overall, so we know it's going to be out of 52. How many 7s are there? Well, we know that there will be a 7 of hearts, a 7 of diamonds, a 7 of spades, and a 7 of clubs. So there should be 4 out of 52. So the probability could be viewed as 4 out of 52. Now, that's totally good, but as we generally avoid simplifying our fractions here. But interestingly enough, if you do simplify the fraction here, you actually get the probability sort of viewed in a different way. So anytime you guys are working on problems, obviously feel free to just leave your fractions as is, but I am just going to briefly mention it here. This is equivalent as a fraction to 1 out of 13. Why is 1 out of 13 important? Well, because you can sort of think about the 7 as being 4 cards out of 52, or you can view the 7 as 1 type out of 13 types. So it sort of is changing how you view the sample space. Here we're viewing the sample space as all 52 cards, in which case it's 4 out of 52, but here we're viewing the sample space as 13 different suits, or 13 different types, and 7s are 1 out of 13 of those. So 2 equivalent answers, but by sort of viewing them as different fractions, we're actually viewing the sample space in different ways. All right, in general, we sort of prefer this one, though, because, again, remember, if you're ever unsure, we always like to think about the sample space as fundamentally as possible, and think about all 52 cards is as fundamental as possible. All right, let's try this one, the probability that we get a heart. Well, for a heart, we can sort of say for each suit, there's these 13 types, so there will be a 2 of hearts, 3 of hearts, 4 hearts, 5 of hearts, 6 of hearts, 7 of hearts, so on. So that means there's going to be 13 hearts out of 52. Right, because there's going to be 1 of each of these types for the hearts. So 13 out of 52. Once again, if we did simplify that, you would be able to find that that's simplified to 1 out of 4. Why is that? Well, we can say that there's 13 cards that have hearts out of 52, or we can say hearts are 1 suit out of 4. So again, that sort of changes the view of the sample space, but it is equally correct in this situation. All right, let's see if we can get the probability of a face card. Well, a face card is sort of a more complicated event. Notice that that really means a jack, queen, or king. So let's think about how we would get that then. So for jack, queen, or king, there's going to be 4 jacks, 4 queens, and 4 kings, because there's a jack of hearts, diamonds, spades, clubs, a queen of hearts, diamonds, spades, clubs, and a king of hearts, diamonds, spades, clubs. Remember, aces, while often important cards in different card games, are not a face card. They don't actually have faces. So it would just be these 4 jacks, 4 queens, and 4 kings. We put those together, 4 plus 4 plus 4, sounds like 12 out of 52. Notice something we're using behind the scenes there is we're just adding these probabilities without any worry of overlap, because there are no cards that are simultaneously jacks and queens, or there are no cards that are simultaneously jacks and kings. So we don't have to worry about any sort of overlap there. So we just added those together. Could we simplify this guy? Well, yeah, if you simplify this fraction, you would get 3 out of 13, which should again make sense because jacks, queens, and kings are 3 out of the 13 types. So 3 out of 13. All right, let's see about the probability that we get a heart and a face card. So if we do this, this would again be what cards are simultaneously hearts and face cards. Well, that would be the jack, queen, and king of hearts, and that's it. So this would simply be 3 out of 52. And again, the reason that we're getting 3 there is because it's the jack of hearts, the queen of hearts, and the king of hearts. Those are the only 3 cards that are hearts and face cards. Notice there's no simplification here because there's no way to view this as another sample space because we're using both suits and types in this discussion, right? In all these other ones, 7 in face card, we were just interested in the types. And for hearts, we were just interested in the suit. Now that we're combining both, we have to use that fundamental description of 52 cards. All right, probability of heart or face card. Well, notice that this is an or. We just found out that there's overlap between hearts and face cards, so we want to use that addition rule. So we do this as the probability of a heart plus the probability of a face card minus the probability of a heart and face card. So notice we can just use all the probabilities. We'll always use the out of 52 so they have the common denominator. So this would be that there were 13 out of 52 hearts plus 12 out of 52 face cards, but there were 3 things that were double counted. Those 3 jack of hearts, queen of hearts, king of hearts, they were counted as hearts. They were counted again as face cards. We want to count them once, but we don't want to count them twice. So we subtract by that overlap, minus 3 over 52, which if you check, you should get 22 out of 52. And again, everything has a nice common denominator, so we're just adding 13 plus 12 is 25, minus 3, 22 out of 52. All right, we've got some other ones to do now. Hopefully we're sort of getting a sense of the idea. The probability of a red and number card. So let's think about how we're going to do that here. So we want it to be red and we want it to be a number card. So for number cards, that means 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many is that? That's 1, 2, 3, 4, 5, 6, 7, 8, 9 number cards. And of course, we'll have those 9 for hearts and those 9 for diamonds. So there'll be 9 heart number cards and 9 diamond number cards. 9 plus 9 gives us 18 out of 52. So there are 18 out of 52 cards that are simultaneously red and number cards. All right, let's try the probability that we get red or a number card. Well, we can do the same thing. We can use the addition rule. We just found out that there's overlap between red and number cards, so we need to be careful here. So red plus the probability of a number card minus the probability of red and number card. Now this time, unlike what we did back up here, we don't already have the answers for these, but we can just go calculate them. For the probability of red, well, we know that that's all the hearts, all the diamonds. There are 13 hearts. There are 13 diamonds, so that means there's 26 red cards. So this is going to be 26 out of 52 plus all of the number cards. Well, we just said that there were 9 number cards. That means there will be 9 for the hearts, 9 for diamonds, 9 for spades, and 9 for clubs. That's 36, because 9 times 4 is 36. 36 out of 52. And then we need to subtract the overlap between red and number cards, which was 18. So minus 18 out of 52. Now here's an interesting little thing. If you forgot to do that overlap and you just did these, you'd get an answer that doesn't make sense, because 26 plus 36 gives you 62. And it wouldn't make sense for a probability to be 62 out of 52, because that's a number greater than 1. And remember, probabilities are always stuck between 0 and 1. So if you forgot this, your answer wouldn't make sense, and you'd sort of remember, oh, I can go back and I have made sure I probably double counted. I need to go back and make sure I account for that double counting. In this case, though, 26 plus 36 minus 18. We can check that on a calculator, of course. 26 plus 36 minus 18. We should get 44 there, so 44 out of 52. All right, we've got another one here. Number card and face card. So we want a card that is both a number card and a face card. Well, are there any cards that are number cards and face cards? Well, no. Right? The number cards are these, the face cards are those. So unfortunately that means that there are none of these. So this would be 0 out of 52, which would be 0. That means number card and face card are mutually exclusive. So that's an example of a pair of events that are mutually exclusive for a deck of cards. There's no card that you could pull out that would be both a number card and a face card. What about the probability of number card or face card? Well, since they have no overlap, we know we can just go ahead and add them. So for number cards, I believe we did that back up here, 36 out of 52. Plus face cards, which I believe we did back up here, which is 12 out of 52. And that would be 48 out of 52. Notice we don't have to worry about subtracting any overlap because we just found out there wasn't any overlap. They were mutually exclusive. Now, interestingly enough, if you sort of think about this, or you try to come up with a clever way, there is a very clever way you can think about this. The only way that you don't get a number card or a face card, the only way that this would not happen is if you got an ace, right? An ace is the only type of card that is not a number card or a face card. So we could actually do this as 1 minus the probability of an ace, because the ace is the only way that this will not happen. This would be using the complement rule. Notice that that would give us 1 minus 4 out of 52, because there are 4 aces, which gives us 48 out of 52, just the same as this. So again, that's another sort of alternate way of thinking about it. That's saying the only way I'm not going to have this happen is by getting an ace. So if I do 1 minus the probability I do get an ace, it'll give me the exact same answer. All right, so this one was just a slightly more sort of complicated version of our first example, but both of these were just trying to help you guys get a few more examples of calculating basic probabilities, as well as using some of these now sort of formally stated rules. All right, we've got one last example to look at, which is still going to give us a little bit more practice with this, but also starts to tie in how this probability stuff can be used with actual data or in a statistics type of setting. So far, we've been studying probability pretty much just on its own. Now let's tie it in a little bit with some data. So this is sort of a quick aside because we're going to continue sort of just viewing probability in terms of probability for a while. We've still got some advanced probability to do, but this is a quick aside or a quick tangent about how to relate probability to some statistics, to some variable type stuff. So this quick aside is on what is called in mathematics or in statistics as a discrete random variable, or sometimes called a discrete probability model. A definition here is that a discrete random variable is a quantitative variable. So there's the statistics element. Remember, a quantitative variable is where each individual is assigned a value, where each value is a whole number. That's what makes it discrete, right? Remember, discrete means that you don't get any sort of values in between. You don't get any fractional values. You just get whole number values. And we know the associated probability of each value occurring. So in other words, we know what is the chance that somebody gets this value, what is the chance that somebody gets that value. So we're going to jump right in and look at an example of this. So we're going to suppose that you're studying the number of vehicles owned by a U.S. family. Now, of course, that is a quantitative variable. The number of vehicles a family owns is a number, and it is a discrete random variable because you can't own 3 1/4 vehicles. You either own 0, 1, 2, 3, 4, etc. So we get the following probability model. So some of the families had 0 vehicles, 1, 2, 3, 4, 5, or 6, and we have the associated probabilities here. So the first thing we're going to do is we're going to confirm this is a probability model. So let's make a note of how we would do that. How do we actually confirm something is a probability model? Remember, way back when we started probability, there are 2 things to confirm. The first is all probabilities are between 0 and 1. Remember, every probability in a probability model must be a number between 0 and 1. Is that the case for all of these? Absolutely. All of these are decimals that are less than 1, and they're all positive numbers, so we're all good with that. Let's give ourselves a little bit more space there. So we're just going to move that over. So the first thing we need to confirm is all probabilities between 0 and 1. We're all good there. And the second thing we needed to check is that the probabilities for all of the distinct outcomes need to add up to 1. So some probability of the outcomes need to equal 1. Well, is that the case? Well, we can check 0.16 plus 0.27 plus 0.33 plus 0.17 plus 0.04 plus 0.02 plus 0.01. Well, we can see 0.16 and 0.27, that sounds like 0.43, plus 0.33, that sounds like 0.76, plus 0.17, that sounds like 0.76 plus 0.17, 86, 0.93, plus 0.04, that's 0.97, plus 0.02, that's 0.99, plus 0.01, that is 1. That does indeed equal 1. Check. So that is confirming that this is indeed a probability model. I mean, you might say, well, it has to be, right? They said probabilities, but we need to confirm, right? A true probability model, everything's between 0 and 1. All the probabilities have to sum up to exactly 1. All right, the next thing we're going to do is we're going to try to draw a probability histogram. Now, we've drawn many histograms earlier on. A probability histogram is very similar. The only difference is that instead of putting the frequencies on the vertical axis, we use the probabilities. Why does that sort of make sense? Well, probability, remember, is a measure of how likely or how frequent something will happen. So, of course, substituting probabilities and frequencies is very normal to do here. So let's go ahead and give ourselves a blank piece, and this will be part B here. So let's go ahead and draw this. So we're going to put the probabilities over here in place of the frequencies. If we look here, the probabilities range from 0.01 up to 0.33, so we need a scale that'll be easy to see all those. So we can go by like 0.05, 0.05, 0.10, 0.15, 0.20, 0.25, 0.30, and 0.35. Also, a little bit different is we're still going to put our variable here. So this is number of vehicles. But of course, because this is discrete, unlike a normal histogram where we would have classes here, we just have individual values. So what we're going to do is we're going to draw our bars, and then we're going to label the middle of each bar with these values. Rather than labeling the endpoints of the classes like we would do for a normal histogram, in a probability histogram, we draw our bars and then we label the middle of each bar with the different values. So let's go ahead and do that. So our first bar should be to 0.16. So let's go ahead and do that. So I'll just go ahead and give myself a little axis. How many bars are we going to need? We're going to need 1, 2, 3, 4, 5, 6, 7 bars. So I'm going to have 1, 2, 3, 4, 5, 6, and 7. That just makes sure that they're all going to be sort of the same size. So the first one is going to be to height of 0.16, and that's going to be the 0 vehicles. Then 0.27. So the 0.27 looks like it would be up here. And again, we're going to label the middle, so that's 1 vehicle. Again, that's a difference because this is discrete rather than when we did histograms for quantitative variables in the past. We had ranges of values. Now we just have a single value. For the next one, we have 0.33. So we're going to put up 0.33. Oh. So 0.33. There we go. Okay, that was for 2. Then for 3 vehicles, it was 0.17. So 0.17 would be right about there. So that was for 3 vehicles. Then for 4, we had 0.04. So that would be just barely under the 0.05. So that's 4 vehicles. And then for 5, we had 0.02. So there we go. So that would be 5 vehicles. And then for 6, we had 0.01. which looks like it'd be right about there, 6 vehicles. Okay, so there is our histogram for that. Right? There's the number of vehicles, the variable, the probability. So if you ever see something mentioning a probability histogram, all that really means is that instead of frequencies, we put the probabilities here, and instead of having the classes as the n's here, we instead just make the n so that each bar is the same size, and then we label the middle as each discrete value. Also keep in mind, notice that the bars are still touching, which is what makes this a histogram, not like a bar graph, which makes sense because remember, bar graphs are for categorical variables, histograms are for quantitative. I think we also wanted to go ahead and describe the shape. So remember, for shapes for us, we have things like we have right skewed, we have things that are left skewed, we have things that fit sort of a bell normal shape, and we have things that are uniform. This guy probably is best. We can sort of see that he's got something that looks like that. So this would be a right skewed distribution. So our shape here is approximately right skewed. And of course, from our general sense of something like number of vehicles, that should make sense, right? Low values of the vehicles, 0, 1, 2, they should be very common. You can't go any lower than 0 in terms of the number of vehicles a family has, but you can of course go much higher with like 4, 5, 6, even though that won't be that frequent. So right skewed sort of makes intuitive sense there. All right, let's see what else we wanted to do. For C, we want to calculate the mean and standard deviation. Now, we haven't seen mean and standard deviation for a while because, of course, that's stuff that we do for variables, for data, right? And for a while, we've been doing probability. So how do we calculate the mean and standard deviation? Well, what we want to do is we want to use these values, but we want to make sure that they're weighted according to how frequently they occur. Things like 1 and 2 have more weight because they have a higher probability, whereas 6 doesn't happen very frequently. So the trick to doing this is that your calculator can do this. We're still going to use our 1 var stat, but we're going to put the number of vehicles into L1 and the probabilities into L2. So if you have your calculator, you can go ahead and do that. So we've got our 0, 1, 2, 3, 4, 5, 6 in L1. And then in L2, next to each of those, we want to have their corresponding probability. So 0.16, 0.27, 0.33, 0.17, plus 0.04, 0.02, and 0.01. So we should have our vehicles in L1, probabilities in L2. So we'll just make a note of that here. So variable into L1, probabilities into L2. Then what we're going to do is we're going to do our traditional stat calc, and then we're going to go to that 1 var stat. Okay. And then what we want to do is, if you have sort of the newer calculator, you'll actually have a place where you can put as the frequency list, you can actually put L2. So you'll want your normal list to be L1, just like always, but you're going to use the frequency list feature for L2. If you have the slightly older TI calculators, what you're going to do is you're just going to manually type in, once you have that 1 var stat, L1, L2. And by typing in L1, L2, you're literally telling the calculator to use this as your list with these as the frequencies. So for the newer ones, you actually have a little option to specify the frequency list. For the older ones, you just have to manually type in L1, L2. Either way, you can then go ahead and calculate once you do that. And what you should get is you should get an X bar that is 1.76. And then interestingly enough, you'll notice that the sample standard deviation is blank. The only standard deviation that's given is the population, which should sort of make sense because when we have a random variable, we have a probability model, which tells us about what happens 100% of the time, because that's what the probability model is telling us. So we are going to, and this is one of the few situations we do this in our class, use the population standard deviation. So for the population standard deviation here, you should get 1.23. What are the units here? Well, of course, we're talking about vehicles. So this would be vehicles here. And then, of course, per family. So we're saying that the average number of vehicles owned is 1.76 and the standard deviation is 1.23. Now, of course, even with a discrete variable where you can only have 0, 1, 2, 3, 4, 5, 6, it's totally fine for the average and standard deviation, which are measures, to be decimals here. Okay, so let's go ahead and finish this up. We've got a couple probabilities here. We want to do the probability that a family has less than the average number of vehicles. So, probability family has less than average. Well, we just found that the average is 1.76. So how would a family have less than the average? That would mean that they have either 0 vehicles or 1 vehicle. That would put them below the average. How would we calculate those probabilities? Well, we just use the probability model. The probability that they have 0 vehicles is 0.16. The probability that they have 1 vehicle is 0.27. So we can just put those together. 0.16 plus 0.27. Notice there's no overlap because you either own 0 or you own 1. You can't own 0 and 1. Doesn't make any sense. So we can add those together and we get 0.43. So we can see that we're basically saying that if we select a family at random, the chance that they have less than the average amount of vehicles is 0.43 or 43%. Keep in mind, probabilities can always be thought about percentages. So in another way, what we're saying is, at least according to the information we have, 43% of families have less than the average amount of vehicles. All right. Now, as a side note, going way back to sort of our quantitative variable work, you might say, shouldn't it be 50%? Shouldn't 50% of people have less than the average, 50% have more? Well, that would be the median, right? The median would guarantee that we have 50% less and 50% more, but the average does not have that trait. So it makes sense here that this value does not necessarily have to be 50%. All right, let's go ahead and look at one more piece, which is that we want to calculate the probability that a U.S. family has at least 1 vehicle. So at least 1 vehicle. Notice that that would mean, for at least 1, that would mean 1, 2, 3, 4, 5, or 6. Now, of course, we could go ahead and add all those probabilities together. So I could just go through and do 0.27 plus 0.33 plus 0.17 plus 0.04 plus 0.02 plus 0.01. But notice it is easier to realize that we're looking for 1 through 6. The only way that that doesn't happen is with 0. So we can use the complement rule and do 1 minus the probability of 0 vehicles, which is 1 minus 0 vehicles has a probability of 0.16. So 1 minus 0.16, which is 0.84. So we can get the probability that a family has at least 1 vehicle is 0.84. Or you can phrase it if you want as a percentage, 84% of U.S. families have at least 1 vehicle. All right, this wraps up our introduction to basic probability. In the next video, we'll be moving into what is called more advanced probability. Generally speaking, advanced probability is probabilities that are calculated either with additional information, which is what we're going to study first, called conditional probability, or probabilities that are associated with multiple things happening, meaning like multiple rolls of a dice, multiple flips of a coin, multiple selections of people from a room or from a group. So we'll study all of that starting in the next video.